Okay, I was asked to do number 7 on internal loads. Um, so let's go through that. Number 7 looks like this. You have a beam that makes a fixed joint with the wall on the right. Um, the whole thing is 0.9 meters long. At the midpoint, you have a torque that goes towards the left. That's 1,500 Newton meters. And then starting at the midpoint, you have this triangular distributed load. That has a maximum value of 15,000 newtons per meter. We're going to ignore the beam's weight and calculate the internal loads. Okay, so the first thing that you notice here is, well, the first step is usually that you calculate the external loads. It turns out if we did the cuts this way, since your cuts never get all the way to the right, those external loads wouldn't come up. So we actually wouldn't have to here, but here's what the problem is. Think for a second about how many cuts we would have. Okay, what would our cuts represent? We have these key points, think of the end points. And then now think of all the places where we have point forces, point couples, point torques. The only one is here. And now think of all the places where the distributed loads change functions. And that happens also at the midpoint, so we don't get any additional points to worry about. So the only place where our subfunctions change for these internal loads is right at that midpoint. So we're going to have 2 cuts for this. Okay, but let's think about what cut 1 would look like. Somebody I talked to noticed that this was a problem, and that was a really good pickup. This is important. So cut 1. Okay, so cut 1 is, the whole thing is 0.9 meters. So this is valid for x's from 0 to 0.45 meters. And so if we draw our cut, draw the piece that we're isolating, that's the part that we are including. Here's all the stuff that we're not. And of the stuff that we're not including, here's the midpoint, right? So that we have this torque is not included in our piece. And also some of this distributed load, notice, is not included. Some is, but some is not. Okay. So that distributed load, the part that we're including, well, let me draw the rest of this stuff on here. So there's the tension, shear force, bending moment, and there's the torque. Okay. We know that at the left end, this distributed load has a value of 15,000 newtons per meter. But at the right end, notice it doesn't go to 0. So by making this cut, we made this distributed load shape not a triangle anymore, because we cut off the point that makes it a triangle. Now it's a trapezoid, and the height of the right end depends on the x value. Okay, so you could calculate this, deal with it as a trapezoid. The way I do it is break it up into a rectangle and a triangle, and then just think of it as 2 different distributed loads and deal with them individually. If you want to figure out how to do that, I think that'd be a good exercise. But let's say that you don't want to do this. So let's say you're like, oh, hell no. Okay, so and it is a mess. Okay, it gets really messy. Is there another way to do this? Yes. The other way to do this is to, so you're looking at this beam, right, from this one side. Get up out of your chair, walk around the beam to the other side, and what you see is this. So now you have the fixed joint there. You have a torque at the midpoint like this that has a value of 1500 Newton meters. And you have a triangular distributed load this way. With a maximum value of 15,000 newtons per meter. Okay. And now when we do the cut where your right endpoint is inside that distributed load, it's still always a triangle. And now we know how to do that. Okay, well, let me go through this calculation, but that's the key here. If you ever have a triangle that's oriented in a way that your cuts would give you a trapezoid, you could do it, but it's really a mathematical exercise. It's better just to think of it, imagine yourself going to the other side and just do the problem that way. You don't get any more or less information either way. It's exactly equivalent. Okay, so the first thing we have to do is calculate the external loads. So do a free body diagram of the whole beam. So you have an unknown force vector at the wall, an unknown reaction couple at the wall. We're applying a torque, so there's also going to be some reaction torque at the wall. I'll call that fancy TR. Okay. We're ignoring the weight. Then we have the torque here. And then we have the distributed load. I'm just going to jump right to, so now that we've chosen what body to isolate, we're isolating the whole thing. Now we can represent that distributed load as a point force. Well, it's going to act 2/3 of the way from the point to the flat side. Okay. The whole length of that triangular distributed load is 0.45. So 2/3 of 0.45 is 0.3. So this distance here is going to be 0.3. And then the magnitude of that force is going to be the area of that distributed load, the area of that triangle. So 15,000 times 0.45 divided by 2. So let me calculate that. 0.45 times 15,000 divided by 2 gives us a total force of 3375. So now Newton's second law, we have the reaction force at the wall. And the only other force we have anywhere is that downward force of 3375. And those have to add up to zeros. And so our force, R, our reaction force, is 0 for X and positive 3375 for Y. That's in newtons. So it's just an upward force at the wall of 3375. And now we have to sum the moments about the x-axis and the z-axis. I don't know why I'm in the habit of doing the z-axis first, but that's what I do. It doesn't matter. You could do it as a vector equation and just throw out the y equation. Let me do it once like that, actually, now that I think about it. You can do it however you want, but I do want you to understand that all I'm doing is summing the moments and setting them equal to 0. Okay, so in the z direction, we have TR, not in the x direction, we have TR. And then in the z direction, we have MR. And then in the x direction, we have positive 1500, 0, 0. And then the last thing that produces a moment, I'm, as always, using my about point at the left end. That's why that force R doesn't produce a moment. But we have a moment about the z-axis produced by that 3375. So that's going to be 0, 0. And then for z, we have a moment arm of 0.45 plus 0.3, so 0.75 times 3375. We have to think about the sign. That would make it rotate clockwise, so this is going to be negative. And all these moments add up to 0. Okay, so what do we get? Well, we get that TR, the reaction torque, is negative 1500 Newton meters. And then we get that MR is positive 0.75 times 3375. So that's 2531.25 Newton meters. Okay, so now we have all our external loads. And we already figured out that we're going to have 2 cuts because we have 1 cut that represents all the x values on that first half and 1 cut that represents all the x values on the second half. Okay, so the first cut is for x values between 0 and 0.45. So the right end of this cut, we haven't gotten to that torque of 1500 yet. We do have all those reactions. So our reactions at the left end are the upward force of 3375. And the moment about the z-axis of positive 2531.25. And then we have the torque. You could draw this as a double arrow going the other way and call it positive 1500, or you can do what I'm going to do here, draw the arrow this way and write it as if this unit vector is multiplied by a value of negative 1500. Okay, so that's a couple. And then the only other things acting are the internal loads. So that's T, V, M, and fancy T. Newton's second law says 0, positive 3375. plus T0 plus 0 negative V. I'll just lump those together. So T negative V is equal to zeros. And so that internal tension on this piece is 0. The shear force on this piece is positive 3375. And now the moment equation. Again, you could do it as a vector. I'm going to go back to the way I'm used to doing it, which is doing the z component first. And then I'll do the x component later. And I said I don't really know why I do z first, but really I guess I do. It's because on beams, it's more common that you don't have a torque than it is that you don't have don't have moments about the z-axis. So I tend to do the torques last because a lot of times you just don't have to deal with those. Okay, so what do we have for moments? Our about point is going to be at the left end. Okay, so we have positive 2531.25. That upward force at the left end doesn't produce a moment because it's through the about point. And then we have plus m minus Vx is equal to 0. And so that tells us that m is equal to Vx minus 2531. And V is given above, so we have 3375x minus 2531.25. And that's our function for the bending moment. And in this problem, we do have torque, so we have to also do this about the x-axis. So the torques, we have negative 1500, and then plus fancy T is equal to 0. And so on this whole, the left half of this beam, the internal torque is positive 1500 Newton meters. Okay, and all of these are valid on the interval of x values from 0 to 0.45. And now we have to do the one where we're inside the distributed load. So cut 2. This one is representing x values that start at 0.45 and go to 0.9, okay? But you have to remember that those x values, each x value just represents a location of the right end of that beam, okay? But our free body diagrams always go all the way from the left end, okay? So we're still going to start all the way at the left end of the beam, but now our free body diagram includes whatever happens at the middle and a little bit past that. So we have the upward force, all this stuff at the left end is still the same. So 3375. We have that torque of negative 1500. And then we have the moment of 2531.25. Okay, but now somewhere before you get to the end, we have this torque of 1500. And we also have part of this distributed load. Okay, but it doesn't get all the way to the end. There's still more there's more beams, so there's more distributed load. So in order to come up with the height of this triangle, we have to come up with the function for this distributed load, as a function of x. Okay, so let's go back here to this picture. All right, well, so what's the function for this distributed load? Well, q of x, okay, because that's what we're looking for, this distributed load function of q of x is equal to mx plus b. Okay, let's come back to b in a second. We'll have to figure out what that is. The slope is the rise over the run of the whole thing. So we can go back to the original triangle, and it's 15,000 divided by a run of 0.45. So 33,333.3 repeating. Okay, so this is 33,333, and then threes go on forever, times x plus b. And now we can come up with b by just choosing a point. We know that q is equal to, you can think of this as like a boundary condition. At the point x equals 0.45, we know that q is equal to 0. So plug in 0 for q, plug in 0.45 for x, and so b is equal to negative 15,000. Okay, so what that tells us is that this function q, our distributed load function, is equal to 33,000. Okay, 33,333x minus 15,000. And so that is the height of this triangle for a given x. The height is 33,333x minus 15,000. Okay. Well, now that we have that, we can figure out for our, now what we need to do is represent that triangle, that triangular distributed load as a point force. To do that, we need the area of that triangle for a given x, and we need the centroid location. Okay, well, the area of that triangle is, so it's going to be, what's the length of that triangle? It's x minus 0.45. The height of that triangle is 33,333x minus 15,000. So that's base times height, and then we have to divide it by 2. And so that area comes out to be, distribute these through, FOIL it, and you get, well, I'm going to do the 1/2 next. So we have 33,333x squared minus 15,000x minus 0.45. Oh, that's minus 15,000x. And then plus 0.45 times 15,000 is 6750. Come on. Okay, we still have to divide all these by 2. So A is equal to 1,667 x squared minus 30,000 divided by 2, 15,000 x plus 3,375. Okay, so that's the magnitude of that distributed load, and the location is, well, it's 0.45 plus 2/3 of the quantity x minus 0.45. All right, so let me redo this free body diagram. We have the upward force of 3375. We have the torque of negative 1500. We have the moment of 2531.25. At the midpoint, we have this point torque of 1500. And then we have this distributed load that we can represent as a point force with a magnitude of 16,667 x squared minus 15,000 x plus 3375. And then the distance from the endpoint here, that's what we're going to need for a moment arm, is 0.45 plus 2/3 of the length of the triangle we have left. So that's 2/3 times the quantity x minus 0.45. Okay. Well, now we have everything we do finally to go to Newton's laws. So Newton's second law says 0, 3375, and then the only other force is that downward force with this crazy complicated magnitude that depends on x. Notice that that is a magnitude. That's always going to be positive for any x's in our range. You can see that by plugging in, any appropriate x's that you want. Plug in x equals 0.6 or x equals 0.8 or whatever, it'll come out positive. And we want it directed in the negative y direction, which means we're going to have 0 for x and then the opposite signs on all these things. So I'm going to write this as 0, negative 16,667 x squared minus 15,000 x plus 3370. Nope, I only did it on the first one. I got to do it on all these. So this should be plus, this should be minus. So now that has the magnitude of the thing in the free body diagram, but it's directed in the negative y direction. And all this tells us that, oh, I got too excited. I didn't put in the internal loads. That's what we're trying to find. The internal loads T, V, M, and torque. Okay, so we have to add on P negative V. Okay, so what we get out of this is that the internal tension is 0, and the internal shear force is negative 16,667 x squared plus 15,000 x. And then we have a plus 3375 minus 3375, so it just comes out to this. Okay. And now we can go to the moment equation. I'll do it about the z-axis first. This is going to be ugly. So what do we have? We have the couple of 25, 31.25. And now we have this force, the force with this magnitude, and it has this moment arm. Okay, so we have the moment arm of 0.45 plus, change this to a bracket, 0.45 plus 2/3 of x minus 0.45 that's the moment arm, and it's multiplied by this force, 16,667 x squared minus 15,000 x plus 3375. And now we have to think about the direction. A downward force there would make it rotate clockwise, so this is minus. And then we have our usual plus m minus vx is equal to 0. Okay, well, let's see. I guess you can think of this as, so we have 25, 31.25. 2/3 of 0.45 is 0.3. So we can think of this whole thing as 0.15 plus 2x over 3. And then we're multiplying it by 16,667 x squared minus 15,000 x plus 3375 plus m minus vx is equal to 0, and our v is the function that's given up there. Okay, I guess keep going. 25, 31.25 minus, so I'm going to multiply all this out, 0.15 times 16,667, that's 2,500, so we have 2,500 plus 0.15 times 15,000. Oh, so that first one is 25. Sorry, I left off the x squared on that first term. That was the 0.15 times the 16,667 x squared. So that is an x squared. The second term is a minus 2250 x. The third term, 0.15 times 3375, is a positive 506.25. And now I've multiplied everything by the 0.15. Now I have to multiply everything by the 2x over 3. So that is plus 11111 x cubed. And then 2x over 3 times negative 15,000x is minus 10,000 x squared. And then 2/3 times 3375 is 2250. So that's plus 2250 x plus m minus vx is equal to 0. Where'd the parentheses end? Right here. Okay, now what can we group together? There are a few things. We can group this with this. We can group this with this. Ooh, and those cancel out. So those are equal and opposite. So we have 2531.25. I'm going to switch the signs of all of these. So negative 11,111 x cubed plus 7,500 x squared. The x terms canceled. Minus 506.25 plus m minus vx is equal to 0. And now I can lump the constants together. So 2531.25 minus 506.25 is 2025. So let's see. So we have 2025 minus 11,111 x cubed plus 7,500 x squared plus m minus vx is equal to 0. Get m by itself, and we have m is equal to vx plus 11,111 x cubed minus 7,500 x squared minus 2025. Okay, well, now we have to plug in for the v. V is negative 16,667 x squared, so m is equal to negative 16,667 x squared times another x, so that's x cubed. And then v is, to get v, add 15,000x and multiply that times another x. So 15,000x x squared. And now we have plus 11,111 x cubed minus 7,500 x squared minus 2025. You can lump some of these together and you get m is equal to negative, what does that come out being? All fives, I think. So negative 5,555.5 repeating x cubed plus 7,500 x squared minus 2025. And all of these are valid on the interval for x. So this is valid on the interval x between 0.45 and 0.9. Well, actually, we still have one to go, but it's the easy one. So now we have to do the moment equation about the x-axis. It's nothing like this last one. So on this one, we just have negative 1,500 plus 1,500 plus t is equal to 0. And so that just tells us that on that second half of the beam, the internal torque is 0. And so now we have a piecewise function that represents the internal tension, internal shear force, internal bending moment, and internal torque over the whole beam. You know, it's broken up into two subfunctions. The last thing I guess we can do that's especially useful in a case like this where you just have crazy numbers of calculations, you have to do it so easy to make a mistake, is we know that for our check, I told you before that for every x value, dm dx has to be equal to v, okay? What I hadn't told you yet is that dv dx has to be equal to negative q. And the reason the negative's there is just because, well, our distributed load function q represents a downward distributed load. So it's just switching the signs there. Okay, so let's take the derivatives and see if it works out. Dm dx, 3 times that is, okay, so negative 16,667 x squared plus 15,000x and that is a constant. The derivative of that is 0. So now compare that to our v function. Yay, it worked. Believe me on this, if we had gotten that wrong, I would not be going back and fixing it. But that's the idea, is that in cases where you have to get the right answer, that's an easy way or a common way to pick up a mistake that you made and go back and fix it. Okay, now dv dx, let's calculate that. So negative 33,333 x plus 15,000. And now we can compare this to, this should be the opposite of the distributed load function that we came up with to start with. So way up here, our distributed load function was positive 33,333x minus 15,000. So it worked out in this case. And that gives you some confidence that things are right. And so these checks, you can always do these. It always has to be the case that dm dx is equal to v and that dv dx is equal to negative q. So you should get in the habit, especially on these complicated problems, of using those checks. One thing that might occur to you then is, well, do we have to go through all this if we know that one is the derivative of the other? Couldn't we just integrate? And you could do that. So say you get once you get your distributed load function, your Q, we got that way long ago. Couldn't we just integrate that to get V and then integrate, multiply by -1 and then integrate that again to get M? And yes, you could do that, but remember that every time you integrate, there's a constant of integration, and we don't know what that constant is. We could solve for it using boundary conditions, but it ends up being, as tedious as this does. It's not really, neither one of these is especially more simple than the other one. So, but if you have time and you want to understand this a little bit better, take one of these problems. I don't know about this one. This one's pretty messy, but take one and see if you can figure out how to get from the distributed load function to the shear force to the bending moment by integrating and solving for those constants of integration. And if you try it and you can't figure it out, send me an email and I'll walk you through it. Okay. So please keep sending questions when you have them. And all right, I'll talk to you soon.